packet ready, it needs to hand it off to someone. And in fact, we kind of glimpsed this a moment ago, at least on a Mac, and Windows and Linux have identical features. If I zoom in here, notice that my computer indeed knows about a router. Its address also starts with 140.247, so that means it belongs to Harvard. And so all my computer has to do via its Ethernet cable or via some Wi-Fi connection is actually temporarily readdress this envelope, not to google.com, but to say, actually send it to 140.247.118.1. And so I still have to mention somewhere on the envelope that the ultimate destination is google.com and its IP address. But for the first hop, so to speak, for the first router, I'm going to say, let me hand it actually to this guy instead. Now, what happens next? Odds are Harvard's router doesn't know where all possible web servers are on the internet, right? They might know Google, but there's some tiny websites out there that they might not know about in advance. So what does Harvard's router likely do upon receiving some packet from little old me? So DNS actually doesn't need to come into play anymore, because at this point in the story, so it's not a bad thought, but we're already talking only in terms of IP addresses. We don't need to work DNS into the picture again. So what would you do? If I hand you a piece of information and say, give this to Matt, what would you do if you don't know who Matt is? Right, maybe you hand it to the person next to you, right? And let them deal with it. And then if he or she doesn't know who Matt is, well, maybe they'll just pass it along. And they'll just pass it along. Now, thankfully, on the internet, it's not necessarily the case that every router knows exactly where Matt is or where google.com is. But because these addresses are number-based, that means that very efficiently, these computers can have the equivalent of like databases or fancy Excel spreadsheets, where in one column is a list of IP addresses that it knows about. And in the other column is a direction. A router, as that picture of a meshed network suggests, actually has a connection usually not just to one other router, but maybe to 2 or 3 or 4. So upon receiving a packet, a router can literally route information left or right or forward or back, up, down, whatever direction the wires are actually going in. And thanks to this routing table inside of its memory, which again, couple columns, IP in one column and direction in the other, well, the router can decide, I don't really know where Matt is, but I know Matt lives on the East Coast, so let me send this packet to a router that's a little closer to the East Coast. And then it can make a similar decision and again and again. And so generally, this takes maybe 10 hops, maybe 30 hops maximally, but the internet's designed to be pretty efficient. So if a packet is going around and around more than 30 times to different routers, usually it gets killed, it gets dropped. And then I, the browser, have to figure out how to get it there more efficiently. So this is all very abstract, but we can actually make this a bit more concrete. I'm going to go ahead and open up the appliance here. And what I've done in advance is I've actually connected to the Harvard Computer Society server. A lot of Harvard's network is firewalled in the sense that you can't do certain things. But if I actually connect to this particular system, I can do more than that. So HCS just refers to that server and my account on it. I'm going to go ahead and do this. I'm going to re-log in, since I did that too long ago. And I'm going to go ahead and run traceroute to, let's say, www.stanford.edu, right? I know that Stanford's out in Palo Alto, but I'm not quite sure exactly how to get it there. But hopefully my computer does. If I go and send an email to some friend who's at Stanford, hopefully my computer can, in fact, trace the route from here to there. So I'm going to go ahead and hit enter. And what we see flying by is a whole bunch of stuff all of a sudden. It looks like 15 lines, 16, 17 lines. So it actually looks like, if we fast forward to the end of this story, that there are 17 hops between me and Stanford University at this moment in time. Or more specifically, between the Harvard Computer Society server, which is also on campus, and Stanford. Why? Well, in step 17, www.lb.stanford.edu is apparently the name of one of Stanford's web servers. LB actually stands for load balancer, so it's some fancier device there. But that server has parenthetically an IP address. It does not start with 140.247 because that belongs to Harvard. This apparently belongs to Stanford. And then on the right-hand side here, what do you think these numbers mean? 3 sets of numbers. What's that? Yeah, the time. So how long did it take for my data, for my packet, for my email, for my instant message, whatever it is I'm trying to do at this moment in time on the internet? It took only 89 milliseconds to travel from here in Cambridge, Mass. to Palo Alto, California, right? And we take this for granted. But if you kind of pause and think about that, like that's kind of mind-blowing. You can only imagine how many hours it takes to physically get a human from Cambridge to Palo Alto. And yet this is 90 milliseconds, right? This is a tenth of a second with which we got this data there. So that's kind of cool. But we can see more along the way. Let's actually trace this route as this command implies. Let me scroll back up to the top, and you'll see that the story started here at step 1. So this is apparently the IP address of HCS's server. That's step 1. And then this one, it doesn't have a name, but it belongs to Harvard just because it starts with the same numbers. And then apparently Harvard passes the data off to this server, which, because the system administrators decided to give it a name, it has a name now. I don't really know where this is, but BDRGW. Anyone want to guess what this shorthand notation means? Actually is border gateway. It's like shorthand notation for a router. A gateway is a router. These are synonyms. Border, it's probably literally on the periphery of Harvard's campus somewhere. And then this has an IP address. As an aside, Harvard also owns a lot of IP addresses that start with 128.103. But this makes sense, right? It only took about 2 milliseconds to go from Sanders, or wherever HCS's server is, to this border gateway. And this, pretty reasonable. 2 milliseconds because we stayed on campus. Contrast this with going to Stanford, which is 3,000 miles away. It's reasonable to expect that it's going to take more time than staying on campus. Well, let's see where my email or my IM or whatever it is I'm trying to do on the internet went to next. Well, in step 4, it goes to knox.org. So this is actually one of these big ISPs, essentially. Northern Crossroads is what Knox stands for. And that's just one of Harvard's peering points. So the system administrators here plug their routers via some kind of fancy cables into this other bigger fish on the internet so that our data has some place to flow. Apparently, Northern Crossroads has multiple routers here and here. But where it gets interesting is in step 7. Where is my data, apparently, at this point in the story? We can only infer, but looks like Kansas. And if I scroll to the right, look at the times. We jumped from like 2 milliseconds up to 30 milliseconds. So it stands to reason that there's a few states geographically in between us. This is a bit of an anomaly, right? It feels like, if my data took 100 milliseconds to get to this point and then 30 milliseconds to get to the next point, these are from the origin points. So realize the internet is not entirely predictable. It could take, some routers rather, could be slower. They could be congested. And so there could be these bottlenecks someplace on the internet. But whatever that issue was, it went away pretty quickly because from here to Kansas, looks like it actually only takes closer to 30 milliseconds. Where are we in step 8? Where's my email now? Houston, probably, and by step 9, Los Angeles, probably, LOSA, I'm guessing. And if we scroll over here, oh dear God, that's quite the detour. Here too, not necessarily consistently the case. And here too, an important takeaway is that if we ran this again, or you ran this tonight or tomorrow, these routes could constantly change. One of the key features of the internet, which is particularly inspired by its military origins, is that it's supposed to be dynamic. These routes can and should change over time, especially if the routers or humans running them determine, wow, this router in Los Angeles is really slow. Let's route around it at this point. And so this can be reconfigured manually or even automatically. So these routes are not hard-coded. In fact, there could be any number of ways to get from here to there. So 10 seems to corroborate the idea that we're in LA because LAX is in the name here. So system administrators have this habit traditionally of using airport codes as the names of their routers. So that's not uncommon to see. I'm not quite sure where this one is, but by step 12, looks like we're somewhere in the campus of Stanford. Then here's another boundary router.stanford.edu. Here's another border router and wowza router. I don't know what this is, but these are just the names they've given to their machines. So long story short, what do all of these lines represent? These literally represent the path that my email or instant message, or in this case, just simulation, took to get from Cambridge to Palo Alto. Well, let's take a look at one other example that's not even to another academic institution. That one was using the Internet 2, which is a faster interconnection among a lot of universities. Let's go ahead and do trace route of www.cnn.com. All right, so enter. And this seems to be going this time from Harvard in steps 1 and 2, and then also 3 and then 4. And then apparently there's some kind of cable between Cambridge and Boston. That's pretty reasonable to expect. Then there's some kind of connection between Boston and in step 7, New York. So that's kind of cool that within 6 milliseconds we can get to Manhattan or thereabouts. This is probably this is Washington, D.C. In step 8 and step 9. Step 10, we're in Atlanta. Step 11, we're still in Atlanta. And then these routers are apparently not responding to our request at this point for privacy reasons or configuration reasons. So you don't always see exactly what's happening. That doesn't mean there's a dead end. It just means that the program I'm using or the special protocol, ICMP, that I'm using to do this simulation, it specifically is blocked, not necessarily web traffic or the like. So one last one, right? Because the numbers here are only interesting insofar as that they're pretty damn fast. 2 milliseconds to DC, 24 milliseconds to Atlanta. Well, let's do an example where we go not to CNN.com, but like ko.jp, which is the Japanese version of their website. And let's hit enter here and see what happens. And it's being a little slower, but we see that this is apparently its IP address. OK, so a few servers weren't responding. And unfortunately, we can't see the magic happening here because in steps 1, 2, 3, 4, 5, let's actually, just for kicks, let's rerun this in case we get better data. Maybe not. But in a moment, we will see, come on. Actually, let's try the other direction. UK. See if this helps. Or not at all. OK. Come on. OK, better. For some reason, it's being pretty slow. All right, so our data is in Boston at the moment. OK, still pretty fast. So this seems to be the network that's just not cooperating. All right, so apparently we're going the long way to London. We're going down to Washington, then down to Atlanta. Then apparently we're kind of hitting that bottleneck here again. So this really isn't demonstrating what I wanted to. So let's try one last time with Japan. Oh, Japan's being better now. So here we go. Now it's 1 or 2 milliseconds to Harvard. There's some good data. All right, so you know, it's kind of sad when you get excited about stuff like this. So let's see here. So we've got some Harvard going on at the top, some more Northern Crossroads, which is in the northeast. I'm not sure where this or number 6 is. 7's just not talking to us. But now 8's getting more interesting. It's apparently in New York City. And this one's cool. This is when you actually do get neat glimpses into the inner workings of the internet. What is in between steps 9 and 10? It's like the entirety of the United States, right? SJC is probably San Jose in California. And so this kind of makes sense if the time to get to step 9 is 27 milliseconds and the time to get to step 10 is 100 milliseconds, suggests that there's some distance there. And actually, what is between steps 11 and 12? Like literally the Pacific Ocean, right? And so there's some huge sub-Pacific cable or cables that are going from the west coast of the US to the east coast of Japan, apparently in Tokyo or thereabouts, between steps 11 and 12. And sure enough, it takes 100 milliseconds to cross the Pacific Ocean. Here too, kind of think back to things we learned in history class, like that's kind of fast to cross an ocean. So anyhow, you can very easily get distracted with this. But hopefully the takeaway here is that what's really happening on the internet is a lot of handing off and off of these virtual envelopes, more technically known as packets, inside of which are messages for the recipient. So what is the recipient going to do? Well, for this, we can actually use a different tool. So I'm still inside of my appliance here, and I've just loaded up